Walking alone, the streets are empty. The only thing I can see is my own silhouette. I'm getting stronger, step by step. The clock is ticking, but there's no time for regrets. I've been flying from town to town, from London to Taiwan. I've been all around the globe, trying to protect your soul. We are heroes tonight. We will fly above the sky. We are heroes tonight. Yeah. We are heroes tonight. We will fly above the sky. We are heroes tonight. Feel like a dynamite, ready to explode right up in the sky. I need you to listen, I need you to hear, and don't show any fear. I've been flying from town to town, from London to Taiwan. I've been all around the globe, trying to protect your soul. We are heroes tonight. We will fly above the sky. We are heroes tonight. Yeah. We are heroes tonight. We will fly above the sky. We are heroes
A very good afternoon to all SPM students. All right, and today we are going to do this Archimedes principle, one of the toughest part in the chapter pressure. Okay, one of the toughest part in chapter pressure, and many students are not able to apply. All right, so I hope you are doing well. How is life going on? All right, I'm sure you are looking forward to going back to school. All right, next week we all will be back to school, and I hope you are getting all the preparation. All right, so this session, which is our clinic from 5 physics, all right, sessions, specially brought to you, is to help you to solve the problem that you may have. All right, in this principle, Archimedes. Okay. So many students will get confused, number one. Number two, all right, they understand half, the other half they don't understand. Right, number three, all right, they are not able to apply. All right, when it comes to calculation, they are not able to apply. So, all right, let me get started, okay? Now, we will not be using the word float, okay? All right, scientifically in Form 5, we use the word submerge. When the whole object is underwater, this is the water level. All right, okay, and you, as you all know, all right, water level, the density of water, I'm going to write down here, all right, is going to be a 1,000 kilogram per meter cube, all right, okay, so if the object is below water, then we will use the word fully submerged, okay, we will use the word fully submerged, all right, fully submerged. But if the object is something like this, all right, we will use the word partially, okay? We will use the word partially submerged. So get it correct, huh? Okay, so point number two. Whenever object is partially submerged or even fully submerged, there will be always two forces acting, all right? Okay, number one, acting downward. Number two, acting upward. I'm sure you know. What's the name of the force that act downward? All right, it is always, all right, it is always weight of the object. All right, it is always the weight of the object. So I'm going to use shortcut weight of object. All right, acting downward, as you can see the arrow there. And now we're going to look at the other one that is acting upward, which is always buoyant force. Okay, all right, buoyant force. You were introduced to it, I think, in from 2. All right, buoyant force. Okay, we will use the symbol FB. Okay, buoyant force. We are going to write like this. Okay, buoyant force. Okay, or in some book they will use the word buoyancy force. All right, it's the same. Okay, buoyant force or buoyancy force. So in bahasa dikenali sebagai daya kapungan. Right? Okay, sebarang objek dalam keadaan separa tenggelam, alright, mengalami dua daya. Satu adalah berat objek yang bertindak ke bawah, satu lagi daya kapungan yang bertindak ke atas. Alright. So, bila dia dalam keadaan terapung, okay, in the situation whether it is here or here or here or here or here, we all know it is in a static position. All right, static. Static means what? Static means they are at rest. Okay, and you know, when object is at rest, the downward force and the upward force will be balanced. Okay, there is no resultant force. Or in other words, resultant force is 0. So we know that in this case, all right, buoyant force will be equivalent to the weight of object. Okay, okay, do I make myself clear? All right, huh? It will be the same. All right, it will be the same. Clear? Right? So I probably just put equal sign here. All right, equal sign here to show you that they are the same. All right, so I don't have to write extra here. And I'm going to give you example so that you can apply. All right, assuming I'm going to give you an object. All right, I press underwater. I give you the volume of the object. All right, volume is going to be, let's say, 1 meter cube. All right, so 1 meter cube is quite big, huh? If it is in a cube, the shape of a cube is 1 meter long, 1 meter wide, and 1 meter high. And 1 meter is this, the length of a meter ruler, approximate 3.3 feet. Okay? All right? Ukuran 1 meter, panjang 1 meter lebar, dan 1 meter tinggi. Clear? Jadi isi padu 1 meter cube. Kita tengok. All right? Diberi juga GSIM, okay, mass of the object. All right? Let me give you, let's say it's going to be a 100. All right? Or maybe 200. All right? 200 kilograms. Okay, right? So I give you this. There is a reason. All right, the reason is I want you to calculate the density. All right, density. All right, I want you to calculate the density of the object. All right, which is going to be given symbol as rho object. And you know equivalent to mass of the object over volume of the object. Okay, boleh have? So we put in the value. All right, mass of the object is going to be 200. All right, and volume of the object is going to be 1 with a unit kilogram at the top. All right, and meter cube at the bottom. All right, then you'll be getting a 200 kilogram per meter cube. All right, and if I were to ask you, all right, whether the object has density higher than water or lower than water, sure you can see. All right, the ball is having lower density. Ketepatan lebih rendah. Why? Because it's only 200. Here it's 1,000. So what happens? All right, this ball, okay, inside water, I let go. All right, I let go. Okay, bila dilepaskan, apa berlaku kepada objek? All right, okay, when I let go, I know. Okay, the object will start to move upward. Okay, huh? All right, huh? Move upward. You must know what happens when you move upward. I'm going to draw another circle here. All right, okay, make sure you know this, huh? When it starts to move up. When it starts to move upward, all right, it simply means buoyant force. All right, buoyant force is more than the weight of the object. Okay, remember that, huh? Remember that. But if it is moving downward, all right, if moving downward, then understood, we know. All right, the downward force, which is the weight of the object, all right, it will be bigger than buoyant force. Okay, kembali. Okay, I repeat, huh? All right, bila objek sedang, the word is sedang, right? Sedang bergerak ke atas, daya keapungan melebihi berat objek. Okay, poin pertama. Poin kedua, apabila objek sedang bergerak turun, then terbalik. Alright, berat objek melebihi daya keapungan. Alright, so in English, okay, we will be using the word, alright, buoyant force more than the weight of the object when the object is moving. When the object is moving upward. When the object is moving downward, then the weight of the object is more than the buoyant force. Is that clear? All right. Huh? So if it's clear, then I'm going to erase the, okay, let it be. So I asked you to check density of the object. All right. You know that it is 200. All right. But density of water is going to be what? Density of water is 1000. So understood. Okay. Object has lower density than water. What happened? When I let go, all right, when I let go, understood. The ball will start to move up. Why? Why is moving up? Understood. All right. Buoyant force is more than the weight of the object, or density of the object is less than density of the water. Is that clear? All right. Huh? So it's clear, then good. So it will rise. I let go, it will rise. All right. Where will it stop? We don't know. Okay. It may stop at position A. It may stop at position B or C or D or E, all right, or F or G. We do not know. Seriously, we do not know. But when we use Archimedes principle, we will know. All right, we will know which position it will stop. Clear? All right. Then we will be able to know. Then let's take a good look. All right. So I need to remove this. Okay. And one more thing. When it reaches either A or B or C or D or E or F or G, we know that the object will stop moving. Okay, it becomes static. All right. When it becomes static, then we know. Okay, we know that. Okay, it will follow this one. Okay, we know that when it becomes static, then we will follow this. All right, equation. What is this equation? All right. When it comes to a stop, we know that we have to follow this equation. All right, and this equation is buoyant force equivalent to the weight of object. So we need to calculate the weight of the object. How do we calculate? Understood? mg. All right, easy job. Okay, all right, mg. Okay, so example 200 kilogram. I'm going to put the word or the number 200 times with a g, which is a 10. All right, so as a result, I'm going to get a 2000 Newton. So what is the use of this 2000? We will use it into the principle known as Archimedes that says buoyant force equivalent to weight of the water displaced. All right. Then I'm going to split this. I'm going to get mg, but it's water. It's water. All right, or liquid. And then I'm going to split this further. All right, by using this formula. All right, by using this formula. All right, density. All right, by using this formula, density of water equivalent to mass of water over volume of water. So it's all water and water and water. All right, and I want the mass of the water as the subject. So what do you see? All right, you will see density of water multiplied with volume of water. So I'm going to take this and substitute here. All right, I will take this and I am going to substitute here. So it will become what? Density of water displaced, volume of water displaced, and finally G. All right, and because we know the value of buoyant force, all right, when the object rises, the object naik, right? It cannot continue moving and moving and moving and moving and moving, right? Cannot be, right? Otherwise, it will be shooting above the water and shoot into the air. All right, shoot into the sky. It cannot be. It will stop. When it stops, we know that this. All right, we know that this will happen. All right, we know that. All right, we know that when it stops moving, this will happen. Clear? This will happen. All right. So in other words, when we know the weight of the object, then we are going to pick the value and put it over here. All right, and then I will know automatically buoyancy force become 2000. So I will take this 2000, I'm going to put it over here. All right, I'm going to put it over here. All right, and I put in density of water, we all know it's 1000. All right, and we're going to, get the value of volume of the water displaced, because this is unknown, times with G, 10. All right, So I will cancel all the zero. All right, basically 1, 2, 3 gone. 1, 2, 3 gone. So you're going to have 10 here times volume of water displaced equals to 2. So volume of water displaced is equivalent to, all right, is equivalent to 2 over 10, which is 0.2 meter cube. So what is the meaning of volume of water, okay, displaced? It means how much volume of the water is taken by the object. All right. How much volume of the object, okay, how much volume of the water is taken by the object. That's the meaning of volume of water displaced. All right. So we all know 0.2 probably is here. All right, it's here. All right, 0.2. Okay, it's here. So the position is going to be G. All right, we all know this one look like 0.2 meter cube, and at the top it looked like 0.8 meter cube. So that you add up 0.3, 0.8 and 0.2, you add up 0.8 and 0.2, you will get volume 1 meter cube again. All right, I think it's pretty clear. So what if I were to double? Okay, we're gonna repeat the whole thing. We are going to repeat the whole thing. What if I were to double this one? Okay, double the mass. I don't want 200. Okay, I cut it off. I want it to be 400. Okay, step number 1, I check density of the object. So I'm going to put a 400 here. I'm going to put a 400 over volume still 1. So I'll be getting a 400. Okay, I'll be getting a 400. Probably I erase this. I will be getting a 400 kilogram per meter cube. And you know, all right, this object is still less dense than water. I let go, it will rise. All right, it will rise. Why? Because density of object less than water. Clear? Where would it stop? We calculate step number 2. All right, we calculate the weight of the object first by putting a mass, which is 400 times 10. I'm going to get a 4,000. All right, and we know when it comes to a stop or static position, buoyant force equals to the weight of the object again. Clear? So we did 4,000. Weight of the object, we're going to put inside here. All right, we're going to put inside here, then you will know. All right, when the weight of the water displaced is 4,000. All right, when the weight of the water displaced is 4,000. All right, then buoyancy force also 4,000. You bring the 4,000 over here. All right, this is buoyancy force. All right, this is buoyancy force. You put it there, then you're going to get a 4,000 here, and you do calculation, you get a 0.4. Is that clear? So we know the position is going to be probably E. It looks like, all right, this is 4 parts, okay, 4 parts, okay, out of 10 parts, right, which is going to be 0.4 meter cube. All right, and up here we know it's going to be 0.6 meter cube because upper portion is bigger. So 0.6 plus 0.4, you'll get back 1 meter cube. Is that clear? All right. So if I were to increase it to 500 kilo, the same volume, object has the same volume, but mass increase to 500. Then again, when you do calculation, you will get the density of the object going to be 500, which is still less than density of water. Clear? So what happens? When I let go, the object still will rise. It will move up until it comes to a stop. When it comes to a stop, all right, this will happen. All right, so before we do this, we have to find the weight of the object. And we know since the mass is 500 kilo, we are going to put a 500 here times 10, then you get a 4,000. And when you get the weight of the object 4,000, right? When you get the weight of the object 5,000, all right, because the mass is 500, all right, 5,000, you're going to take this and put it over here, all right? The weight of the object 5,000, then, okay, all right, automatically you will be able to see that the buoyant force becomes 5,000. And with this number, you're going to put it here, then you'll be able to see, all right, the calculation will give you 0.5. What does it mean? It means half of the object is underwater, right? It will be probably here, all right, half. So I will okay, shake this one, all right? So this one look as though the bottom part is 0.5 meter cube, all right, and upper part will be 0.5, okay? So you see the object keep on moving from higher position to lower and lower somehow because density of the object keep increasing. All right, why does the density of the object keep increasing? Because I increase the mass of the object, all right, from 200, all right, to 400 kilo. All right, I repeat, I increase the mass of the object from 200 kilo to 400 kilo to now 500 kilo, right? 500 kilo. That's why density of the object keep on getting higher. When density of the object keep on getting higher, it will eventually submerge at a lower position. All right. So I'm going to show you the last one. Let me repeat one more time. If I increase the mass to 800, all right, which position would it be? We can calculate by using, all right, the formula, okay, discovered by Archimedes. Archimedes, all right, is a physicist. They come up, okay, with this, okay, principle known as Archimedes principle. All right, so 800 kilo. Then step number one, okay, check density of the object. We know that we put a 800, all right, as a mass, all right, okay, over 1 meter cube, you get a 800. Number is bigger, but it's still less dense than water. It's still less than water. When you let go, the object will rise. Okay, but when it rises, it will finally come to a stop somewhere. Clear? All right. Then we want to find out where it stops. The second step is we will find the weight of the object. With a mass 800, then we will substitute 800 as the mass times 10. You get an 8,000. All right. And when the object comes to a stop, okay, whatever position, we know that buoyant force equals to the weight of the object. All right. With the weight of the object 8,000, you're going to put 8,000 here. All right. Therefore, you know the buoyant force is 8,000. You will take this one and put it over here. Then when you continue completing your calculation, you will know that the weight, sorry, the volume of the water displaced, it will be 0.8. All right. And tell me which position it will look like 0.8 meter cube is below water. I repeat, which position will tell you, all right, which position will tell you the object has a volume, all right, of water displaced equal to 0.8. Can you put into our chat box so that we know, all right, whether you are able to, comprehend this principle known as Archimedes? Which position would it be? So those of you who are looking at our, our live, okay, all right, our live through Zoom. Can anybody respond? Which position would it be? Would it be A? All right, would it be B or C or D or E or F or G? All right, when we have the mass of, all right, some of you will probably say A, some of you will probably say B. All right, perhaps A and B is very close. All right, maybe I will draw this one a little bit lower. All right, maybe I will draw this a little bit lower so that probably you will see, all right, probably you will see only a small portion is below. All right, maybe you see a smaller portion is below water. All right, so this is a new position of A, all right, and B and C and D. All right, so probably you can see this. Okay, at the top is approximate 10%. This one probably is a better one. Agree? All right. So okay, that means that you all, if you are able to answer me correctly, so it simply means that you start to comprehend. So this is the answer 0.8 meter cube. All right, at the bottom. All right. This is the volume of water displaced, and this is the one 0.2. All right, meter cube. Okay. So I guess everybody would have grabbed the idea. So I give you one more example, so that you know how to apply. Okay. So I'm going to erase all this. All right. If you want to have reference, please, okay, do a screenshot. All right. Do a screenshot before I erase this page off. I only give you 2 pages today. All right. Or for this very special session, because Archimedes is a very, very tough part. Reason why they moved this chapter pressure into Form 5, all right, into Form 5 for the first time is because of Archimedes. Clear? All right. So I'm going to give you 5 seconds. 5, 4, 3, 2, 1. Okay, there you go. I'm going to erase all this. So I'm going to look at only one particular question, all right, to apply Archimedes principle. Okay. All right. And this is something that probably perhaps you have been exposed to. All right. Simple one. I'm going to give you a spring balance. All right, which is going to hang an object. All right. Okay. With initial reading of 80 Newton, okay? all right, it is going to show you, okay, the indicator show us here, all right, the indicator show us here 80 Newton, okay, all right, when you are hanging the object in the air, all right, similar diagram, all right, will be shown to you, all right, they show, okay, similar spring balance, all right, hanging the object, all right, but the object is going to be what? Submerged in water, all right. So in other words, it's the same exact drawing, except of course, all right, I'm going to put a beaker here, all right, I'm going to put a beaker here, all right, so I'm going to have some water placed here, all right, okay, and I'm going to put what? The reading now, all right, to show you the reading is going to be 60 Newton, all right. So I'm sure you've come across this type of question, all right, I'm pretty sure you've come across this type of question, it's very, very common, all right. So the question they may ask you is number one, find buoyancy force, right? Number one, I'm going to write down here. All right. Question number one, find FB, buoyant force. All right. Number two, they ask you to find the weight, all right, the volume of water displaced. All right. Volume. Okay. Probably I may ask you the weight first. Okay. I probably ask you weight of water displaced. All right. I write in blue color, weight of water displaced. And number three, I'm going to ask you volume of water displaced. Okay. All right. Okay. Step number one. All right. Step number one, I'm going to ask you what is buoyancy force. We're going to do this one first. Very simple. From 80 Newton, it becomes 60 Newton. All right. Surely buoyancy force will be 20 because buoyancy force is the only force that push upward that actually make 80 to become 60. All right. So you probably can tell the answer. All right. So I'm going to put the answer here. All right. The answer here. All right. For part one, buoyant force equivalent to, all right, okay, 60 Newton. Yes, correct. But examiner won't be happy if you show this because examiner demand what? Working. So I always wanted students to write down the working. All right. Now, when this reading is showing 80, it simply means, all right, it simply means the tension is also 80. All right. Tension 80. All right. And the weight of the object is also 80. All right. Easy job. All right. That's why the whole system is balanced. 80 downward, 80 upwards. 80 downward, 80 upwards. All right. 80 Newton downwards, 80 Newton upwards. The system is what? In a state of equilibrium. All right. That's why it is at rest. Now you're going to do the same thing. It's not difficult at all. Look here. 60 Newton, that means the tension here is also going to be 60. All right. And the weight, object is the same. All right. Object is the same. Understood. We have got the same weight. All right. Which is going to be what? 80. And we have buoyant force, okay, which is acting upward. And we do not know what is the value of the buoyant force. I'm going to write down here. I will probably put it here. Okay. All right. This is the weight of the object. All right. And this is going to be buoyant force. All right. One acting downward, one acting upward. Okay. Very simple. One acting down, one acting up. All right. I'm going to write again one more time. All right. One acting down and one acting up. All right. So this is going to be buoyant force. All right. So I always tell students, all right, to apply this very simple. Okay. Because the system is balanced in a state of equilibrium, the upward force are always equal to downward force. All right. Downward force is only one, weight of the object. All right. Weight of the object is downward force. All right. So you're going to put weight of the object here. And the value we also know 80. All right. And upward force, we know we got two. The one that I put in red color. First is tension of the string. Second one is buoyant force. So I'm going to put down tension plus buoyant force. All right. Then substitute tension. All right. 60. Tension equals to 60 into here. So 60 plus weight, buoyant force. So understood. You could see very clearly why the answer it is going to be. All right. Why the answer is, sorry. Oh, okay. I put the wrong thing here. All right. Okay. I guess it's covered. All right. It should be 20, right? Should be 20, right? From 80 becomes 60. Understood. Buoyant force is 20. All right. I'm sure you know that, right? Okay. But nobody gives me any comment. All right. I repeat one more time. Original weight 80. right? Original weight is 80, all right? But when you place the object in water, it becomes 60. So understood, there will be something they push up, all right? And that something is called buoyant force. And how much was it, all right? Understood, 80 minus 60, agree? All right, 80 minus 60, you know, is going to be a 20, all right? Okay, I put wrongly just now the number, I put a 60, but nobody gave any comment, all right? Okay, I hope you are paying attention, all right? If you know there is a mistake, you have to let me know, all right? Letting me know meaning that you are one step further, okay? All right, you can detect the mistake. So 80 minus 60, all right? You get a 20, but calculation you need to show like this, clear? All right, okay? I repeat, downward force is the weight, all right? Downward force is the weight of the object, 80 Newton. Upward force for two, one is tension, all right? One is tension, one is buoyant force, all right? So tension we know is 60. Buoyant force, then we calculate, we will bring the 60 to the right side. Then you know that it's going to be 80 minus 60, then you end up getting 20. And this will be the same answer that we get here. All right, is that correct? Okay, boleh ha? So we have done part one. All right, we have done part one already. We're going to do part two. All right, part two says, find the weight of water displaced. All right, weight of water displaced is here, it's here. This is the weight of water displaced. Now, this one, clear? And it's equal to buoyant force. And you know, buoyant force is 20 Newton. So understood, you know, your answer for the second part, weight of water displaced is equivalent to 20. All right, you can present your answer, part two. You can present your answer, part two here. All right, because of the fact buoyant force is equal to the weight of water displaced. All right, and the question asks you, what is the weight of water displaced? Then understood, you will write what the other side, giving you buoyancy force here, and you know the value of buoyancy force, which is 20 Newton. There you go. This is going to be your answer for the weight of water displaced. Is that clear, people? So I got the answer for part two already. It is still going to be the same. Weight of water displaced, all right, equivalent to 20 Newton. Third one, all right, volume of water displaced, all right. I'm sure you will be, okay, able to pinpoint which equation to use. It's none other than this one, clear? It's none other than this one, all right. Archimedes principle tells us that buoyant force equal to the weight of water displaced, weight of water equal to mg. All right, mass of water equals to rho of water times volume of water times g. So we do a checklist. All right, we know this value. Okay, buoyant force. We know it's a 20. All right. We also know weight. We also know density of water. Here, density of water. All right, 1,000. And we also know the value of g. All right. So only this we don't know, and that is exactly what the question asks for. Right, volume of water displaced. Okay. Right. So we're going to get an answer for volume of water displaced very soon. It will be another, okay, maybe 2 minutes. Clear? So I substitute, buoyant force, we know it's going to be 20. Density of water, we know it's a 1,000. All right. Volume of water displaced, we know it's going to be, right, an unknown. All right. And G is going to be a 10. All right. So understood. We're going to cancel the the 0 here and a 0 here. Clear? So you end up having volume of water displaced equivalent to a 2 over 1,000. And you put it in standard form, it will be a 2 times 10 power negative 3 meter cube. Okay, that's it. You would have come to the end of today's very special session, a session that will be able to make you understand and be able to help you to apply the principle known as Archimedes principle. Clear? All right. This is a very popular. All right. Every science student must know this principle, and in the exam, okay, they always will focus. Right? They will always focus on this principle. Right? And many students, okay, maybe they understand, but okay, not very sure, right? Not very sure how to apply. Boleh? I repeat, buoyant force equals to weight of water displaced equals to mg equals to rho, v, and g. So when you calculate and you get 2 over 1,000, it simply means the volume of the water displaced is 2 times 10 power negative 3 meter cube. You may think that, why the number is so small? Because the unit is in meter cube. So we bring this number here. All right, we're going to write the answer here. 2 times 10 power negative 3 meter cube. All right. So with this, we come to the end of today's session. All right. I will meet you then the following week, which I'm going to do another slot the same day, the same time, but it's going to be Form 4. All right. And since you're in Form 5, I hope you will join our slot, right, so that you will get a thorough revision, all right, from the beginning of the year now until the end of the year. All right. Please like, follow, and share, all right, our slot, okay, right, in our Facebook, so that this good news will go to as many students as possible. All right, whether okay, those people okay are your friends or people whom you may not know, it'd be good if you are able to share, okay, right, and like our posting, okay. So with that, okay, I will come to the end of our session. I hope you have a good coverage on Archimedes principle. All right, it's a very popular in SPM. All the best to you. Okay, bye bye, and okay, all the best. Right.